In this video, we'll be talking about line integrals with respect to arc length. So let's start with a curve C. Could be either in 2D or 3D, depending on the context. And we're going to look at a little tiny chunk of the arc length along this curve, which we're going to call ds. The type of integral that we're going to be trying to integrate here is the integral along the curve C of some function f times ds. Let's suppose this curve C represents a wire with density delta. Then we can talk about a few physical features of this wire, such as its length, its mass, the coordinates of its centroid, and its moments of inertia. So let's look at some of these formulas. If we wanted the arc length, in symbol we call that s, and to get that arc length we would integrate along our curve C, and what we'd integrate is just ds. If we wanted the mass of our curve, let's call that m, then we would integrate along the curve. What we'd integrate is the density function. We can look at the coordinates of the centroid of this wire. X bar would be 1 over the mass times the integral along our curve of x delta ds, and similarly we could get y bar and z bar. So for z bar, for example, we take 1 over our mass times the integral along our curve of z delta ds. We can also talk about the moments of inertia with respect to the 3 axes. So if we want the moment of inertia with respect to the x-axis, we would take the integral along our curve C of y squared plus z squared delta ds. And similarly, we could look at the other 2 moments of inertia with respect to the other 2 axes. And in each case, our integrand is going to be the sum of the squares of the other 2 variables. So for I sub y, integrand would be x squared plus z squared delta ds. So there we have our formulas for our moments of inertia, our centroid, mass, and arc length for a wire with a given density. These integrands are the same as the integrands that we used for double and triple integration earlier in this video series. So we're now just applying them in a slightly different physical context where we've got a wire with known density. In order to get into a calculation, what we need is a formula for how we're actually going to calculate ds. So there are going to be 2 variations here depending whether we're in 2D or 3D. So we'll write down both variations. If we're in 2D, then ds is going to be the square root of dx by dt squared plus dy by dt squared, and then outside the root here we're multiplying by dt, so that's the 2D version. And the 3D version, quite similar, it's just got an extra term under the root corresponding to the z variable. Before we jump into an example, let's draw a quick picture and try to understand where this formula for ds comes from. I think that this will be most clear if we just look at the 2D example. So let's just ask, why is this formula true? Looking at the 2D formula. Well, imagine that we've got a curve C, and what ds represents is just a tiny, infinitely small chunk of the arc length along C. So if we actually zoom in on ds, we could say over a very tiny interval, ds is basically a straight line segment. So let's say that's ds there. And that ds includes a little bit of change in the x direction and a little bit of change in the y direction, which we'll call dx and dy. So by the Pythagorean theorem, we could say ds is going to be the square root of dx squared plus dy squared. So we could take this quantity and we could multiply it by dt over dt. And let's take that factor of dt that we're seeing in the denominator and let's bring that inside the square root. So when we bring that inside the square root, that's now going to become a dt squared in our denominators. So under the root, we're going to have dx squared over dt squared plus dy squared over dt squared, and then we still got that factor of dt out at the back. So with a little bit of bracketing, that's going to look like the formula that we wrote down above. So we could say under the root, we've got dx by dt squared plus dy by dt squared, and then that's times dt. So that all goes towards justifying these formulas for ds that we wrote up a little bit earlier here. And these formulas are what we're going to need if we actually want to do a computation for a line integral with respect to arc length. So we mentioned at the beginning of this video that we're going to be computing integrals of the form integral over some curve of some function times ds. So all these types of integrals that we've written down here. And these types of integrals where we're integrating along a curve are called line integrals. Despite the fact that our curve may not be a straight line, we still call the integral a line integral. I suppose curve integral might be a better name or a better way of thinking about it, but line integral is just the historical name for this type of integral. So anytime we see these integrals where we say we're integrating along C, just picture a curve, could be in 2D or 3D. So here's an example of how we compute a line integral with respect to arc length. What we want to do in this example is find the mass of the wire with given density function, where the wire is described by the following curve. So we've got this curve in 3D. We're describing how the x, y, and z coordinates change as the t values range from 0 to 2. So basically at t equals 0, we're mapping out some point in space. At t equal 2, we're mapping out some other point. And then as those t values vary, our curve is moving in some way through three-dimensional space. So the first thing we're going to work towards here is coming up with a formula for ds. We're going to need that in order to set up the integral for the mass of the wire. So let's start by taking the derivatives of our different x, y, and z variables here, taking our derivatives with respect to t. So dx by dt is going to be 1. dy by dt, well, we would have 4/3 times 3/2 t to the 1/2. So let's just call that 2t to the 1/2. And dz by dt is going to be t. So with that, we can break out our formula for ds. So as we said above, ds is going to be a certain square root times dt. Under the square root, we're going to have the sum of the squares of these different derivatives. So the dx by dt squared plus the dy by dt squared plus the dz by dt squared. So let's sub everything in here and get a nicer formula for our ds. So just squaring each of our derivatives and summing up, we're going to have 1 plus the square of dy by dt is going to be 4t. And then plus the square of dz by dt, that's going to be t squared. And that's all times dt. So now we can say mass is going to be the integral along our curve of delta ds. So in other words, integrating along our curve, we were told in the question that our density function was x plus 2. So we'll just sub that in there. And then that's times ds still. So in order to turn this into an integral that we can calculate, the idea is to move everything over into the variable t. So there are three things we want to transform over to t. We want to change the limits of integration over to t. We want to change our integrand and also our ds. So here's where our formula for ds above comes into play. We'll be able to just substitute in there to get ds in terms of t. To get the x plus 2 in terms of t, we can look back to our problem. Remember, we were given formulas for how x, y, and z depend on t. So we can just replace our integrand with the appropriate functions in terms of t. And then to get our limits of integration, again, those would be given as part of the problem. T would be ranging between 0 and 2. So I think we're ready to plug everything in and get this switched over to the variable t. So we said t is going to be ranging from 0 to 2. We were told that for this specific wire or this specific curve, x is equal to t. So our integrand becomes t plus 2. And then our ds is the square root, 1 plus 4t plus t squared times dt. So we've now got an integral entirely phrased in terms of t, and we're ready to proceed with the integration. So let's try a substitution here to get this done. Let's sub u equal the quantity under the root. That would make du equal to 4 plus 2t times dt, and that means that du over 2 is equal to 2 plus t times dt. So for the sake of our substitution, let's say we're trying to compute the indefinite integral of t plus 2 times this root times dt. And we're going to say, well, that's the same thing as integrating root u, and then the t plus 2 times the dt we said is the same thing as du over 2. So let's write this as 1/2 the integral of root u du. And then we can say, well, integrating the root u, we're going to have u to the 3/2 times 2/3. And we can say plus c, just because that's good form with indefinite integrals. And then we can write down our answer. So that would be 1/3 times something to the power 3/2, where the something is our u. So the 1 plus 4t plus t squared. And then we'd have our plus c on here just for good measure. So with that, we're ready to finish off our integration. And I think I'll just write our final answer up here just below our integral. So our integration gives us 1/3, 1 plus 4t plus t squared to the power 3/2, and we're going to evaluate that at t equal 2 and then t equals 0. Well, both of our expressions are going to have the 1/3 on there, so we might as well factor that out. And then subbing in t equal 2, we'd have 13 to the 3/2, and then subtracting off our value at t equals 0, we'd have 1. So what that's giving us is the mass of the wire with given density function, where the wire has a prescribed shape. So we were told what the points x, y, and z were along that curve. And the way that we actually computed the mass of that wire was by setting up this line integral. Line integral just being a fancy way of saying, hey, we're integrating along all the different points along some curve. And you can do that in either 2D or 3D. So I wanted to finish this video with just a little bit of terminology. In this video, we were looking at integrals like the integral along some curve c of some function times ds. And when you see an integral like that, that's properly called a line integral with respect to arc length. So that's in contrast to something like integral along c of something that has the form, say, p dx plus q dy plus r dz, where p, q, and r would be some functions involving x, y, and z. Something like this is called a line integral with respect to coordinates. And we'll talk about these line integrals with respect to coordinates in an upcoming video. So when we say that our line integral is with respect to arc length, we're just saying that the differential we're seeing on there is ds. Whereas when we say that we've got a line integral with respect to coordinates, then we're saying that we're seeing a dx, dy, and possibly dz term inside that line integral. So think of these line integrals with respect to arc length as being useful when you're trying to get some physical attribute of the curve itself. For example, if you imagine that curve to be something like a wire with a prescribed density, then you can talk about the mass of that wire, the centroid, the moment of inertia with respect to the various axes, etc.